video we are going to wrap up 3.1 quadratic functions. And we're starting here with example 5. We're not going to learn anything new. These are just more real-life applications to the stuff we've already learned. Many applied problems involve finding the maximum or minimum value of a quadratic function, as well as where that value occurs. So here in example 5, we got a football punt. The figure over here, 3-7, shows that when a football is kicked, the nearest defensive player is 6 feet from the point of impact with the kicker's foot. So here, 6 feet away from the kicker, we got this defender. He's going to come up in part B. The height of the punt, f of x, in feet is modeled by this quadratic, negative 0.01x squared plus 1.18x plus 2, where x is the horizontal distance in feet from the point of impact with the kicker's foot. Okay, now in these type of problems, usually the hardest thing is trying to figure out what the heck they're asking you to find. So I'm going to move this up here a little bit. I'll drag it down so I can see the picture in a little bit. I just want to be able to see this function. Okay, part A. What is the maximum height of the punt and how far from the point of impact does it occur? If you want to, pause the video and think about that a minute. What exactly are they asking us to find? The maximum height of the punt and how far it is from the point of impact does this occur? You can always, make a little sketch to try to figure out what's going on. Here's our XY axis. Here's the punter. Hey, he's going to drop the ball and kick it about 2 feet off the ground. Whoa. And then the ball, of course, is going to travel up and then come down. So it says, what's the maximum height of the punt? Well, we know a maximum is going to be the highest point on that curve. And how far from the point of impact does it occur? So it looks like, how far from the point of impact will be this distance. And then how high the ball goes up is this distance. So this is just the vertex of our parabola. They're just asking us to find the vertex, but they're asking it in a different way, applicable to this problem about our football. So they're just asking us to find the vertex. The vertex, as we have been learning, is negative b over 2a. So negative, our b is 1.18. We have 2 times a, which is negative 0.01. And we could just punch that in the old calculator. Of course, the negatives will cancel out. And if you punch that in, you will find it is equal to 59. And we're dealing with feet here. So that's 59 feet. We know our vertex has an x-coordinate of 59. So is that the height of the ball or the distance from the kicker's point of impact? I'll let you think about that as we find the y value. How do we find the y value? Well, that's just f of 59. We're going to run that 59 through the function and see what pops out to take up the y value. So that's going to be 0.01 times 59 squared plus 1.18 times 59 plus 2. And if you punch that in the calculator and do everything right, you will get 36.81. 36.81 feet. So that'll go in here, 36.81. All right, back to the question. What's the maximum height of the punt and how far from the point of impact does it occur? So one of these numbers is the height, the other is how far from the point of impact. Of course, the y value is our height. That's what we measure on the y-axis. The punt's going to go up and come down. So this height is over on the y-axis. That's the 36.81. And that height occurs at a distance of 59 feet from the kicker. So we've answered part A. And we found the vertex. Part B. How far must the nearest defender player, who's 6 feet from the kicker's point of impact, reach to block the punt? So again, we got our kicker here just right about at the origin, and he's going to kick up and come down. And 6 feet away, we have a defender. He's standing here, and when the ball's punted, he's going to reach up, maybe jump a little bit, and try to block the punt. How far must the nearest defense player be to reach, or how far must the nearest defensive player reach up to block the punt? How are we going to find that, or what are they asking us to find? Again, pause the video and think about it. Well, they're saying, if this player is 6 feet from the kicker and the punt's going to go over his head, how high would he have to reach up to get a finger on that ball and block the punt? So what they want us to find is just f of 6. And that will give us our height on the y-axis. So for part B, we're just going to find f of 6. Negative 0.01 times 6 squared plus 1.18 times 6 plus 2. You know, play along at home, punch that in your calculator and see what you get. Calculator skill is part of the class. You got to know how to push the buttons. And if you work that all out, it is 8.72 feet. And you know, if you are provided with a picture, sometimes you can use that just to get an idea if you're close. So if we look here, you know, this player's 6 feet away. If I follow the graph paper grid up, I'm going to hit here, and if I go over to the y-axis, it looks like a number a little bit less than 9, and yeah, that's our answer. Number a little bit less than 9. Perfect. All right. Question C. If the ball is not blocked by the defensive player, how far downfield will it go before it hits the ground? What are they asking us to find? We've found this before. They're just asking about it in a different way. Kicker's going to kick it. We're going to go up, hit our max, and then we're going to come down. How far away down the field will the ball go before it hits the ground? So what is this? Well, that's just an x-intercept. They want us to find the x-intercepts of the function. And how do we do that? Well, let's see. We try to factor it if we can. So here's our equation. And we want to set it equal to 0. Okay, with this negative 0.01, you know, trying to factor that, you know, just by plugging in some numbers and trying, that's definitely not going to work out. If we want to do complete the square, we're going to have to divide every term by negative 0.01 to get this to be a positive 1x squared before we can complete the square. Probably the easier way to go is going to be the quadratic formula. X equals negative b plus and minus the square root of the quantity b squared minus 4 times a times c, all divided by 2 times a. So there you go. The decimals are kind of nasty and stuff, but just bust out your calculator and work it through. The way I usually do these is to find what's going on under the radical first. I'd punch in 1.18 and square it, and then minus 4 times negative 0.01 times 2 and hit equals and find what's under the radical. And then I would square root that and write the number down. And then I'd, you know, do the negative 1.18 plus that and divide it by the denominator, and then the negative 1.18 minus that quantity and divide it by the denominator. Again, just to save time in the video here, I'll let you do all that number crunching on the calculator at home, and I really encourage you to try it because, again, pushing those buttons does take a skill, and that's something you got to practice also. You might have the concept down, but actually getting the answer you might run into a little trouble. So if you do this all correctly, you're going to get two answers, a negative 1.7 and 119.7. Okay, let's think about this. One of these answers, of course, does not make sense. How far did the ball go down the field before it hits the ground? Well, did the guy kick it and the ball went backwards, maybe a breeze caught it, and it landed behind him, or 1.7 feet? No, that doesn't make sense. We have an answer that does not make sense in the context of our problem. So he kicked the ball, it goes up, comes down, hits the ground 119.7 feet from where he kicked it. Again, it was just the quadratic formula. If possible, you can complete the square, but usually with all those decimals, it might be easier to go with quadratic. Okay, for part D in this problem or in any homework problem, when it says graph the function and we're dealing with numbers, you know, that big, I would just do a bare bones approach. We know we have an x-intercept here on the negative side. That's negative 1.7. We know we hit the x-axis. We'll go over here. That's our 119.7. And then I can draw my parabola. See, the y-intercept is easy enough to find. That's just going to be 2. And then we know our max here occurred at the vertex. And our vertex was 59 on the x-axis, comma, and then our height was 36.81. So when they say sketch a graph, you know, that's good enough right there. As long as we see all the key parts, the intercepts, x and y, and the vertex, and, you know, that's all the important stuff that you find in a parabola. Okay. Example 7. Another neat application of these are maximizing and minimizing different things. If you do go on to calculus, we do a nice full section just on all types of different types of problems about minimizing and maximizing. So you have 100 yards of fence to enclose a rectangular region. Find the dimension of the rectangle to maximize enclosed area. And what is this max area? All right, we want to cordon off a rectangle with 100 yards or 100 feet, or yeah, it's 100 yards, 100 yards of fencing. Let's take it to the extreme. Maybe this side is 1, this side is 1, so that leaves 48 feet for the other. If we add up the perimeter would be 100, and the area of this rectangle would be 1 times 48 is 48 feet squared, or yards squared, or whatever unit. Okay, well, that's not the best way to come up with a rectangle. And actually, I shouldn't be doing that. Well, yeah, I guess I could. We could do 20, 20, 30, 30. That perimeter also adds up to 100. And let's see what the area is here. Length times width would be 20 times 30, or 600. Look at that. With the same amount of fencing, we could fence off 48 square feet. Or if we change the dimensions, we're now up to 600 square feet. And actually, we can go a little higher than that. There is a sweet spot to this where we want to find a maximized area. And we'll talk more about the graph of this and the graphical explanation as the problem goes on. Oop, I don't want to do that. Oop, there we go. So we got 100 yards of fence to enclose a rectangle. We want to maximize the area. Step 1, decide what you want to maximize or minimize. Well, here it says maximize the area. So we want to maximize area, and the area of a triangle, or rectangle, excuse me, is length times width, or let's just call it x times y. Call this x, and we'll call this y. Okay, in calculus, we call this our primary. That's the most important equation. That's what we want to maximize or minimize. In step 2, they want us to express this quantity as a function in a single variable. Because right now we have two variables, x's and y's. And it's going to be not easy to solve unless we get it down to one variable. Well, I don't think the book goes into a good enough explanation as to how do you get it down to one variable. Well, we need a secondary equation. Something else that is relative to the problem that will also unite the variables x and y in a different way. Well, in this one, we have 100 yards of fencing, and we know we can find the perimeter of a rectangle. The perimeter is, we add up all the sides, length times width, or length plus width plus width again. If we want to add up all the way around, we will get the perimeter. Perimeter equals, for this rectangle, would be 2x plus 2y. So that's the perimeter of any rectangle, and we know our perimeter is set in stone at 100 yards. So we're going to set that equal to 100. All right. Now at this point, we want to solve for one variable or the other. Doesn't matter. You can't go wrong at this part. We could solve for x or solve for y. I'm just going to solve for y. So to get y by itself, I'm going to subtract 2x from each side. And now I'm going to divide each term by 2. Y equals 50 minus x. Okay, now here is how we get that equation down to one variable. Our area was x times y. Well, if we know y is equal to this quantity, we're going to take that quantity and plug it in for this y. So now our formula can be written as area equals x times, and instead of this y, again, we're going to sub in 50 minus x. So that's step 2. Express this quantity as a function in one variable. Again, in calculus, you'll hear primary and secondary equation. Primary, that's what we want to maximize or minimize. The secondary is just another equation that we can use to get our primary down to one variable. So now we're down to just x's. All right, what's the next step? Step 3, write this function in the form of a quadratic. X term and x, or x squared term, x term, and the constant. So let's see, it looks like we're going to have to distribute the x. X times 50 is 50x. X times negative x is minus x squared. And it's not truly in the proper form until the x squared term is first. So the x squared is going to go here. Now notice too, the negative is with the x squared. So that's going to stay with the x squared. This 50 has an implied positive in front of it. So it's x squared, negative x squared plus 50x. So that's step 3. We put it into proper form. Now step 4, we're not finding the whole vertex, we just want that nice x value. We only need the x value of that vertex. So x equals negative b over 2a. Well, our b is 50, and 2 times a, our a is here in front of the x, and there's an implied 1 there, negative 1. So it looks like what we have if we put the negative up there with the 50, negative 50 divided by negative 2 is 25. So we know x, we know this side of the rectangle has to be 25. Okay, now how do we find the y value that goes with it? I did erase it, but back when we were getting it all down to a single variable, we did have this, y equals 50 minus x. Well, okay, if we know x is 25, we just plug it right in here. Y equals 50 minus 25. 50 minus 25 is 25. So our rectangle isn't actually going to, well, it's going to be a rectangle, but a special rectangle with all equal sides, which is a square. So our length and width are each 25. Did that answer the question? It says answer the question posed by the problem. So we did find the dimensions, but the final answer is, what's the max area? Okay, well, area equals x times y, length times width. 25 times 25 is 625. We're talking yards, yards squared. So to maximize our area, we'd want to use 25 on each side of the rectangle or the square, so that would be our 100 feet, and we would have the most area in our fence. All right, good times, good times. Now time for some practice. The first checkpoint problem is very much like the football problem. We got an archer. His arrow is being shot up in the air. It's going to follow a parabolic path. The height of the arrow is modeled by this quadratic, where x is the arrow's horizontal distance in feet. Notice here, this is a lot like example 5, but example 5 had A, B, C, D. This only has A, B, C. So one of the things you were hunting for in the example is not here. See if you can figure out which one it is. So pause the video, try these examples or practice problems, and then fire it back up and see how you did. Okay, let's see what we got here. Archer's arrows fall on a parabolic path. For part A, what is the max height of the arrow and how far from its release did this occur? Okay, well here's our XY axis, and right here about at the origin, we got our bowman. He's got a little bow and arrow, and he's going to shoot his arrow, and of course it's going to go up, and it's going to come back down, it's going to hit the ground. So they are asking us for the maximum height of the arrow, which of course will be some value on our y-axis, and how far from the bowman did that maximum occur? Well, that's going to be our x. So that would be our vertex. Got to find the vertex just like the football problem. So part A, we want to find our vertex. Start by finding our x value. X is negative b divided by 2 times a. So the negatives, we can cancel those right now. And then we're going to have 2 divided by 0.01. And that's going to equal 200. So that's the x value of our vertex. Okay, how do we find the y value? Well, we just evaluate the function at that number. F of 200 is going to be negative 0.005 times 200 squared plus 2 times 200 plus 5. If you do all this right, do the squaring first, of course, times the negative 0.005, add 400, then add 5. It comes out to be a nice, I believe it's 205. Yes, 205. So that's our y value. That's the height, the maximum height of the arrow. Okay. So I guess that finishes off part A, max height, how far from the release. There it is. I already got those numbers written down on the picture, so I'll erase that. Part B. Find the horizontal distance the arrow travels before it hits the ground, round to the nearest foot. So that arrow, of course, gravity will bring it back down. It's going to hit the ground somewhere. How do we find this point? Well, that's an x-intercept. And how do we find x-intercepts? Well, we set the function equal to 0. Negative 0.005 x squared plus 2x plus 5, and set it equal to 0. We're not going to factor it by guessing and checking. Complete the square might be possible, but we'd have to divide every term by negative 0.005, and it's going to turn into a pretty big number mess. Might just want to, again, stick with the quadratic. X equals negative b plus and minus the quantity of b squared minus 4 times a times c, all divided by 2 times a. So work that out on your calculator. Again, I highly encourage you to do that. You should be practicing that skill with everything else. And if you get everything punched in there right, you do get two answers because of the plus minus, of course. One of them is negative 2.5, and the other one is 402.5. Well, let's see. If you're going to shoot an arrow, is that arrow going to go up and then land behind you? Well, maybe if you're a real bad shot or there's a strong wind, I guess. That could be possible. But this is the nonsense answer that does not fit the context of the problem. The 402.5, and again, I think we are in feet. Yes, we are in feet. That's how far the arrow went before it hit the ground. 402.5. There we go. C, graph the function that models the arrow's parabolic path. Again, I've been doing that sort of as we go along. All important information is there. I guess we could do our y-intercept. The y-intercept would be 5. So if my parabola continues down, that would be 5. And then my other x-intercept, that would be the negative 2.5 right here. But again, that is a nonsense answer to our problem. And I think that's it. Again, if you want to compare this to the football problem, there was something else. ABC here was really A, C, D. In the football problem, the part B was there was some guy trying to block the football. Now, I can see trying to jump up and block a football, but would anybody really want to try to, stand here and when this guy's going to shoot his arrow, jump up and block the arrow? No, I don't think that's going to happen. So they left that part out of this example problem. All right. Now this is, I should find a better checkpoint question for this. This is exactly the same thing as we did, but they just changed the amount of fence you have now to 120 feet. You're still enclosing a rectangular region. You want to find the dimensions to maximize the area and find that area. So again, we got those steps. One, what do we want to maximize or minimize? Again, if you can make it to calculus, this is called our primary equation, and that's what we want to minimize or maximize. And here again, we are maximizing area. Area equals x times y, or length times width. 2, we want to write that equation in terms of one variable, and we can only do that with the aid of a secondary equation. Just like the example, it is the perimeter. 2x plus 2y, those are the lengths of our sides. We have two sides of x, two sides of y. They're going to add up to 120 feet. Well, we could divide by 2 right now. X plus y equals 60. In the other one, we solved for y. Let's solve this one for x. Why not? X equals, we'll subtract y from each side. 60 minus y. So this 60 minus y can take the place of x. It's going to go right there. So now we can write area equals y times 60 minus y. And maybe when you were doing this, if you really pause the video and then are checking, oh, that should be an x. What's going on there? 60 minus y. Whoa, back. There we are. So that's part 2. We got our primary equation down to one variable. Step 3 is to put it in standard form. So we're going to distribute this y, and then we're going to have a negative y squared, which I'll put first, and then plus 60y. Ooh, I guess we should have left the variables alone because, well, it shouldn't matter either way. Let's just keep plowing along. I guess if I screw it up, I'll just start the video over. So there's our equation. And now, of course, we want to find the vertex. Ooh, I wonder if this will work. Oops. Vertex equals negative b over 2 times a. And in front of that, there's a negative there, so there's an implied 1, negative 1. And then we're going to get negative 60. Yeah, this will work. Over negative 2. And if we divide that out, we get 30. So back to our rectangle, we have our x and y. We found y is equal to 30. Well, let's find x. We did get to the point where we wrote x was 60 minus y. So x equals 60 minus 30, which is 30. So again, we have maximized our rectangle by turning it into a square. Each side is 30, So what is our area going to be to maximize? 30 times 30 is 900. 900 is this feet? Yes, 900 feet squared. There we go. Now for homework, oops, stop that. A couple problems from these pages. It's number 59 and 66. If you got the notes from me in class, I did just print those out. 59 is on the front, 66 is on the back. I made it into a worksheet. The picture gives away everything you need on 66. It is a better fence problem in my opinion, because now you're building a fence along a river, and you're not going to wall off this side of the river. The book went a little far. You have 200 feet of fence, and they said call these X. Well, if you got 200 feet of fence, I mean, you've used up a couple X's. What do you got left? 200 minus 2X. Again, that picture should be right on the packet that you got in the problem, or if you're going to copy this out of the book, it'll be right in the book. All right, I'll see you in the next video.